All right, good morning, everybody. In my previous hour, I've had some issues with the stream being a little stuttery. So let me know if that persists. Then I will put up my backup recording. But hopefully, between Discord or YouTube, one of them should hopefully work. Just as a check, can everybody see and hear what's happening? Um, If I'm quiet, it could be on your end as well, perhaps, because everything on my end is maxed. So there's no way for me to turn it up any louder, but I will double check. Yeah, everything is maxed on my end, so I don't know what to tell you. But I have checked the YouTube videos that can be watched after the fact, and the sound is good there. If it's really something you can't hear. Often, if you have an external headphone set, it has its own volume, and that sometimes can boost things as well. But there are so many different volume sliders in all kinds of places sometimes that it's easy to miss one. There you go. Click on me and boost my volume. Or it could be a setting somewhere. It's hard to know. But everything on my end is maxed, and most people seem to be able to manage. All right. Let us continue with our slides. Now, we've done most of it. I think we can get away with one more lecture to be done. If you remember, we looked at platonic solids, where we are allowing one regular polygon face that can be repeated. We can have triangles, three coming together at a point, four coming together at a point, or five coming together at a point to make vertices of the polyhedra. We can have three square faces coming together, or we can have three pentagon faces coming together. Now, of course, you've spent the whole of yesterday practicing these drawings and the names and everything because there's not much else to do, I guess. And we have a relationship between the number of vertices, faces, and edges called Euler's formula that allows me to just know two of the three, and I'm able to find the other one, whichever two will be the easiest or maybe be given. Now, when I think about representing polyhedra, be it a platonic solid or something fancier we'll see, I have some options. I have a name for it, like icosahedron, tetrahedron, and so on. I can make an actual physical three-dimensional object, a physical model. That would have been portfolio assignment number 5, but we had to be in class to get the materials, so that is scrapped. We can make a drawing on a piece of paper or a flat surface that we've practiced. And we can also represent the polyhedron by way of the net. Now, the net isn't the easiest thing to work with, so we mentioned the concept and then looked at the cube and let it go after that. I want to spend a little time looking at the word part, the verbal representation, the name for these polyhedra. Why is it called a tetrahedron, octahedron, icosahedron, and so on? Well, seeing as the Greeks were some of the first people to really be intrigued and uh, spent a lot of time studying this. They came up with the naming system that was sort of carried through even to our time still. So we try and hold on to those, to the Greek language and how they named the shapes, um, just for the tradition, if nothing else. So because tetra means four, I have four sides. I have four faces, rather, not sides. Faces. They call this a tetrahedron. Four faces. The octahedron, eight faces. Icosahedron, we'll see icosy means 20, and this polyhedron has 20 faces. Now the cube is a new name, so I'm not sure exactly how that evolved. Dodecahedron, we'll see dodeca means 12, and this polyhedron has 12 faces. So it's actually quite simple that the number of faces isn't really something I need to memorize, it's in the name. But I have to know the Greek numbers. So there is some logic to this in that the number of faces is the word that is used in the name of these shapes because they were the first shapes to be discovered rather. Uh, and it, but as more things got discovered, the naming system got a little less efficient. But uh, we were so used to it at that stage that we still try to hold on to that. When things got a little bit more complicated, the inherent properties of the polyhedron uh, is sometimes used to add more words to it. Now that can become very complicated, but at the basic level, we have the Greek number prefix and then the root uh, for the faces word. For example, dodeca is the word for 12, which is a 2 and a 10. It's sort of a special one, and that will be used to describe the 12 faced, not sided. It's a typo there. Put my hand over it. 12 faced polyhedron. Icosy means 20 for the 20-sided icosahedron. In that case, the I changes to an A. I'm not an expert on the Greek language at all. That's just the way it is. And this isn't necessarily the Greek language right now. It's what they used back then. Following this pattern, we can call the cube a hexahedron because it has 6 faces. So an alternative name for the cube is a hexahedron. Now, as things get more complicated, they discovered that there can be, in some cases, multiple polyhedra with the same number of faces, unfortunately, when I relax the regular requirement and things like that. Then a name can be put in front to indicate the kinds of faces. Even though I have a dodecahedron, the original dodecahedron, if we scroll up, the first dodecahedron had pentagon faces. There are other more complicated 12-sided polyhedra that have different kinds of faces, like a square or a rhombus is the slightly more general name. And then they put the word rhombic in front to distinguish this one from the classic Platonic solid. So because the naming system came from a time where there weren't many of these polyhedra discovered, as more were discovered, the naming system became less elegant, less efficient, and a little bit of a mess. But the tradition was already established, and people were trying to hold on to that system. So if you have 24 faces, for example, you can put a name in front. We'll get to the naming system, the numbers in a second. You can put a name in front to indicate what kind of face you have in that shape when there are multiple with the same total number of faces. All right. So now our goal is to move the polar bear away. Right. Good point. Let's see what I can do here. Luckily for the next bit, it doesn't matter. I don't want to deny the polar bear his place in this. Okay, so our goal is to learn the Greek prefixes or the Greek number system names for their numbers. Now we've seen some of these before. Up to, I think, 12 we have seen in our discussion on tessellations. Excuse me. We have seen tetra, penta, hexa, hepta, octa, meaning the numbers 4, 5, and so on. Deca is 10, hendeca is 11, dodeca is 12, dodeca meaning 2 and 10. Dodeca is a little special. Then, I apologize for the screaming children in the background if you can hear them. They don't really know their own volume. Then once I get to the other teens, the higher teens, we can use the word chi to link 3 and 10. And then chi means and. So 13, it's backwards. 13 means, or we're going to say 13. Okay, hold on. Something froze, something froze. Hold on. YouTube stream's okay. Yeah, something just froze, I see. Let me, my screen's back, everything's back. Where did you lose me? Not much happened before this slide. Our goal is to learn the Greek prefixes because that is going to tell us immediately how many faces there will be in my shape. And that's one of the 3 things I need to know. So by just understanding how to interpret the name of the polyhedron, I will get from that the number of faces. And then I can only worry about vertices and edges to know everything. But in order to get the number of faces out, I have to understand the Greek number system or naming of the numbers. So from our tessellation discussion, we've already seen everything up to 12. 12 being dodeca, meaning 2 and 10. Dodeca is a little simpler, well, not simpler, rather special, because after that, the teens have the system for 13, for example, it's 3 and 10. So triskaideka, the first part, the S is sort of a connector letter. Tri meaning 3, chi meaning and deca being 10. So in the Greek system, it's backwards, like more than one European country. Anything sort of Germanic based, the numbers are said backwards. For us, at least. For them, it's not backwards. The ones are said first. So it's 3 and 10, 4 and 10, 5 and 10, hexakideca, 6 and 10. So it's just a combination of the earlier 1 to 10 words. 18 uses the word for 8 and linking it to 10, 8 and 10. Just to check, since there was some disconnect issues, is everyone with me right now? No one ever loves this table, but it is necessary. And I'm not saying that this is the Greek language right now. This is what came from the Greek language way back that we're still using when we call when we name these polyhedra. Okay, so now the system is sort of set. When I go up to different tens, I just have to have a new name for 20, 30, 40, 50, 60, and so on. And we're not going to go into the triple digits. We'll stop below 100. I think the S in Triskaideka is just to make it sound good. It happens often in language that you put a letter in between so that the word flows and sounds better. But I am in no way a linguist. Maybe there is another reason for that. Same if I look at 20, the word is icasa, as in icosahedron, 20-sided polyhedron. But in other situations, the A can be an I, and there's probably a linguistic reason for that. I am not even going to pretend to know. We are not going to be uptight with this at all. So if you, for example, in 13 don't have the S, then it's totally fine. This is not a language class. 20 is icasa, as in icosahedron. Icosahedron, 20-sided polyhedron. So I don't want to go too fast, so please comment and give feedback because this table is not a favorite uh, really anytime. But it's going to tell me my number of faces. When I just see the name of a shape, I can use this table to know exactly how many faces it has without even seeing the shape. So if I, for example, have, oh, so let's just go through the tens. 30 will be, we can just say triconta. So the conta means I'm in the tens, so three tens, in a different way, 30. I don't want to use deca for that because that's used for 13. So a new word, piece, is conta to tell me I'm in 30. Tetraconta, 40. Pentaconta, 50, and so on. So I'm using the 3, 4, 5, 6, 7, but with conta meaning I'm in that multiple of 10. So let's write some stuff down. I don't love the exercises we have in the book, so we're just going to make our own. Nope, get out. There we go. So let's just make a new page here. So that we can write some examples, but you are correct. So we now have two goals. We can say the number to the Greek name and then back and forth. Let's say Greek prefix. So for example, if I say 34, that's going to be 4 and 30. Now, this isn't maybe at the time the system was created, there was only one way to say it, but we are going to be as relaxed as possible and not be too strict. So if you have the pieces roughly there, uh, it's going to be correct. We're not going to look for necessarily one answer. So for example, which one do I have? 34. You can say 34 as tetratrichonta because it's 4 and 30. Let's write that down. But if you want to put a chi in the middle, because that sounds better to you, that's going to be totally fine as well. We want to be as relaxed as possible and just get the concept across. What other number could we have? Maybe like an 85. Now my table is not memorized yet, perhaps. 85, I said. All I have to remember is that the ones come first and then the tens. So it's opposite to how we would say the number. 85 would be penta octaconta. Now you can put a chi in between, but it's not necessary. Whatever sounds good to you. Maybe there is a linguistic issue with the vowels being next to each other. If it sounds better to you, put a chi in between. I am not going to be very rigid or strict with any of this. It's just the idea. Maybe, yeah, the chi might be an option because linguistically they might not allow the two vowels. Maybe that changes something because the chi just means an and. So use the chi freely however you want. So it takes a while perhaps to get comfortable with this, but I have to just remember that I know a lot of these single names for the ones already. Penta, hexa, hepta, and so on. Go full screen here. Then it's not about memorizing as much as understanding the system that the ones come first. So, for example, if you say 13 as trideca, that's going to be acceptable for us as well. You don't have to remember the S, you don't have to use the chi, don't use the chi, whatever sounds good to you. As long as we follow the basic rule, ones, then tens. And then it's just a matter of how do we write the multiples of 10 with the conta. So there's really very little to remember when you think about this. Initially, it seems very overwhelming, but there's very little to remember. It's my basic numbers up to 10. Sure, 11 and 12 might be a little bit special, perhaps. After that, I just have to remember the multiples of 10 and put the ones first. Any questions on that? So I'm trying to memorize as little as possible, and I feel there are only, in addition to the single words, so to speak, up to 12, there's really only the multiples of 10, which really has one word, conta, and then I remember the ones come first, opposite to how we say it, and that's pretty much it. Any questions at this point? It might take a while, but once you look at it a little bit, it's not as strange as it might originally seem. We're only going to put two together because we have a ones and a tens to make a two-digit number. Once you go into the hundreds, well, that's a different story I don't really want to mess with. So a quiz question could be, represent or give a Greek name because we're going to be relaxed for 48, for example. Then I just remember the 8 comes first. It's 8 and 40, octa, tetrachanta, or whatever version you want as long as the 8 comes first. But I still have a two-digit number, so two pieces are put together. Or what is the number that corresponds to, for example, let's go with trihexaconta. What is the number of faces in a trihexacontagon? Hedron, sorry, trihexacontahedron. What would you say in chat is that number of, if it exists, a trihexacontahedron? So it's really not bad. It's 63. Or let's try another one. Uh, let's say tetraheptacontahedron. Tetraheptacontahedron. So remember the ones come first, or I could say tetrachiheptacontahedron. That would be 74 because it's 4 tetra and then the 70 heptaconta. So the only key thing I have to remember is that the ones come first in the two-digit number, because these are the prefixes for the polyhedron, and they tell me how many faces are in the polyhedron. It's not the Greek language as it is today. It's the naming system for the three-dimensional shapes. Yeah, using chi might be nice for a separation between ones and tens for sure. All right, so that is a possible question, because the main question is the number of vertices, number of faces, number of edges. And the number of faces is now in the name. So I need to interpret the name to get one of these three, the faces. Now let's look at something else before I go to the next slide. Well, I went there anyway. Let's go back and look at our platonic solids again. Let me see if I can open that. Let's look at the cube. I need to get a way smaller pen. That's not bad. Okay, cube time. In a regular polyhedron, what happens at a vertex is the same for every vertex. So just like in the case of a tessellation, I can have a vertex figure name. It's my pen. I'm struggling to write very clearly with this bottom pen, but it's the smallest one. Vertex figure name. It's going to be done in the same way by focusing on a vertex, and then I'm going to represent the faces that occur around it. It's a square face, and that has name 4, another square face, another square face. Now you can condense that, but I'm not going to bother with that. So I can give a more symbolic name again for these three-dimensional shapes by simply describing what happens around a vertex. How do the faces come together and what faces come together? For example, the dodecahedron has vertex figure name. I'll just put it up here. Uh, 5 dot 5 dot 5. With this pen, my 5 has a little curly tail because the pentagon has name 5 and there are 3 of them coming together. The icosahedron, I look at any vertex that's comfortable for me, something in front that I can see all the faces. That's going to have vertex figure name 3 dot 3 dot 3 dot 3 dot 3. I can condense that as 3 with a superscript 5. It's not an exponent, it's not a calculation, it's just a name, but I can just list them as well. It's never going to be that much to list in a row. So I have the vertex figure name as an option to name the polyhedron because we're now going to relax the requirement that I can only use one kind of face. And then it's a matter of how do they fit together. It's not a times or a plus or anything, it's just a separator between the face names. All right, so if we relax the requirement that I can have only one polygon as a face in my polyhedron, we then open it up and have different kinds of polyhedron classifications. But this is going to be where we stop. Just like for tessellations, we opened it up to semi-regular tessellations, and then we saw, oh, there are 8 of them, there's some variety. This could go further, but let's stop there. We get the idea. This is going to be the same. We have our 5 regular polyhedra, the platonic solids. We go one step further to see what can be done, and that hints at a whole world that we only sort of peek through the crack. So it now splits up into a couple of groups of polyhedra. The most important one, I would say, is the truncated polyhedra. So I want to think of the process of making this shape from a platonic solid. You pick one of the 5 platonic solids. For example, pick the cube. Pick the cube, for example. What we're then going to do is we're going to cut off the corners. We're going to slice them off. And what that creates when I cut off this front corner of the cube is a triangle. So I do that for every corner of the cube, back and the bottom and all the way around. Every time when I slice it off, I create a triangle face, the yellow ones. In the process of doing that, my original red square face becomes an octagon. So I now have a new polyhedron with triangle faces, the yellow ones, and octagon faces, the red ones. Did any of that make sense? I know you're speechless. Yeah. So I want to think of it as a process. I can take any platonic solid. The cube is the easiest one for us to start with right now. Slice off the corners. That's a new polyhedron And by that action, I've created different kinds of faces. So let's see if I can write on this. So here, the number of faces is now my original cube faces. So let's do it this way. Sorry, let me let me back up. Original, the original cube had the original cube had 6 faces. What is exercise 16.3? Oh, sure, we could do that. Let me zoom in here. Yeah, we've missed exercise 16.3. The vertex figure name of a pretend polyhedron with the following faces around it. Let me just do it right on this. Why not? Okay, so here we have a triangle, and then a square. That'll be 3.3.4. Ah. Then we have a triangle, a triangle, and a square coming together. That will be 3 for the triangle, 4 for the square, 3 for the triangle, 4 for the square. And then we have 5 triangles coming together. That would be 3.3.3 5 times. Vertex figure name is not the Greek name. No, no. That would be these kinds of questions. Determine the name of the hypothetical polyhedra with the following number of faces. There's a name and there's a vertex figure name. But in the question in the future, in a quiz, I'll emphasize the Greek prefix name. Uh, let's actually do these. We're here, why not? So what's the number that corresponds to tetracantahedron? That's 4t. So that's 40. 40. And then hexatricantahedron will be 6 and 30, 36. Octachioctahedron, 88. Everyone happy with those? No, no one? All right. Then the Greek name corresponding to 34. We've done 34. Tetra, tricantahedron. Or use the chi as freely as you want. 18. 18 is actually on my table, so that's pretty easy. Now you could just, if you just say octadecahedron, I don't care about that for our purposes, as long as the ones come first. 53, that's 3 and 50. As long as you have the ones first and then the 50. Let's see, still confused why we're adding hedron to the end. Because this is only the Greek prefixes for the polyhedra. You don't have to, but I am doing that to emphasize this is not a Greek language class. The Greek language uh, these days is not exactly like this. We are focusing on polyhedra. This 34-faced shape is a single polyhedron. So it has this, whoops, that many faces. All right, so now we're caught up. It doesn't matter if we're going to go into tomorrow to be sure about what is coming up. Truncated. Okay. Back to truncation, which is a little complicated, but very important. Okay. So it's coming from the cube in this example. I know the cube has 6 faces and vertices. How many vertices does the cube have? Now, luckily it's the cube, so I can just imagine it. I have 8 vertices. If I'm looking at edges, I don't have to count the edges. I use Euler's formula. The number of faces plus the number of vertices will always be 2 more than the number of faces. 6 plus 8 is 14. Number of edges is therefore 12. I don't have to put in a lot of effort. And the edges number is often the more difficult one. So I try and get faces and vertices, and then the edges are calculated with my equation. If I try and count edges in the more complicated shapes, I'm going to make a mistake. So now, in the truncated cube, if we go back to our, whoop, where is our platonic solids? There's our platonic solids. Cube, edges, let me make a hand here. Add. Edges, 1, 2, 3, 4 for the top. 1, 2, 3, 4 for the bottom. And 4 on the side. That's 3 times 4 is 12. I want to find the edge number, which means if I solve for E in Euler's formula, I really move the 2 to the other side, so it's vertices plus faces minus 2. I don't add 2 on top, maybe that's what you did. But you can look at the cube. We picked the cube for a reason to start with, that I can just look at a very simple drawing and literally go around counting the edges, and I'll get 12. Or am I not understanding your question? Do you see the cube? Let's zoom in on the cube. Well, now my polar bear's behind the cube. There's the cube. We're looking for edges. If you don't want to use the formula, you can just count the edges. Top 4, bottom 4, 4 on the side. That's 3 times 4 is 12. So I can confirm, equation aside, it has to be 12. But if I want to use the formula, let's just make some space here. Let's go back to my slide. Where's my slide now? Here. Let's use text. So here, if this is my equation, which it is, I have 6 plus 8 on the left, that's 14. What should E be so that it's 14 on the right? It has to be 12. You have to minus the 2. But for simple shapes, I have some background noise here. That's nice. Hold on. All right, sorry about that. Okay, so 12. I'd like to just finish the truncated cube, and then we'll build on this, and we eventually have to truncate all of them. Now for the truncated cube, if I understand what truncation does, I can use my numbers from the cube to understand that my original cube faces are still there. So excuse me, I have 6, 6, no, what was that? I don't know what that was. 6 plus, because I cut off the corner, the vertices, I cut off the corners as well. Each of those original cube corners are now faces in the truncated cube. I originally have in the cube 8 vertices, and now I've created faces from them, so I have 8 more faces. So the truncated cube has a total of 14 faces. Now, I will admit, do not be shy to ask as many questions as you want, because truncation is not obvious to everyone. It's something I have to get used to. But I want to emphasize my best chance to succeed is to understand the platonic solid that it's coming from. Know those numbers first, then what does the action of truncation do, and how can I use those numbers? That is the key here. Is everyone happy with 14 faces of the truncated cube? So then next up is obviously vertices. Now originally the cube had 8 vertices. What did I do to create the truncated cube? I sliced off that vertex, and in that process I've created 3 new vertices. So for every one original vertex of the cube, for every one original corner point, I've now created 3. So the new number of faces is 3 times the old one. So the truncated cube has 24 vertices. How's that? Now, am I going to count the edges? Not even a little bit, I'm going to use my formula, which is, for our purposes, always going to be true. I have the vertices, sorry, I have the faces plus the vertices. Let me move this to the side. Euler's formula is still true. So that means whatever the left-hand side is, faces plus vertices, which will be 14 plus 24, so that's 38. So 38 on the left. What is the edge number? So I get 38 on the right. Has to be 36. There's no need to count edges. Just use Euler's formula. It is by far the most efficient. But in order to do that, I need to bring the cube numbers to get the new face number and vertices number for the truncated cube. I can only have one thing missing in Euler's formula. So our goal moving into tomorrow is to understand where the truncated cube numbers come from, because we have to be able to truncate any one of the Platonic solids. Now the cube is a good starting point because it's the simplest. Tomorrow we can start by truncating the tetrahedron, and you'll see in the problems, not the problems. In the problems I have here truncating an octahedron. I have to be able to truncate each of the Platonic solids. So we start with the cube because it's simple, and then we will maybe do a tetrahedron. Maybe that's the next simplest one. And eventually we want to be able to get all the properties of any truncated Platonic solid to really understand what this truncation is doing, and in that process create 5 more potentially polyhedra. So we have a question: why is the edges 36 and not 38? So on the left, let me do it this way. On the left side, let's put it over there. On the left side of Euler's formula, I have my faces 14, my vertices 24, and that gives me 38. So on the right side, I need 38 as well. So if the number of edges plus 2 gives me an answer of 38, what is the number of edges? It's 38 minus 2, so 36. So I'm always going to...
All right.
All
I
right,
don't.
someone speaking. Yay.
I really don't understand what you're saying. I thought like, where does the plus two? So I thought to get edges, you had to do faces, vertices plus two, and I got your edges.
No, look at Euler's formula.
I am.
I'm trying to
I
find
think
it
you
too. Oh,
lost
there
me.
it is. Okay. So the equal sign separates the sides, right? The E is
Uh
on the
huh.
other side, and the 2 is on the other side.
Uh
So
huh.
the left side is vertices plus faces. Then I get an
Okay.
answer.
And that gives you your edges,
No,
right?
that gives me the left side's answer. That,
Okay.
in order for the equation to balance, has to be the answer when I take the number of edges and I add 2. So in our case, the answer is 38 for the left
Okay.
side. So if I have a mystery number of edges, I add 2, I have to get 38. What is that mystery number? It has to be smaller.
Oh, so
It just takes a while. It's all good.
I know, but so okay, so when you want to get your number of edges, so what's the plus two do? Like, I can't find my papers here. Like, this plus two
The
is that
plus
supposed to give you your edges?
no, the plus two is to balance this equation.
Okay,
The
yeah, but the
edges
final. Go ahead.
the edges isn't exactly the same as the vertices plus the faces. There's a two difference between the two. So the two is there to balance this equation, and then the equation is always true. So if I have the vertices and the faces, I add those up, that's the left side of the balance.
Okay.
So the right side is the number of edges plus two. That has those two sides have to equal each other. In our case, 38.
Okay, so when you do number of so e edges plus two, what does that give you?
It has to give me the 38.
No, 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 no. What does that number represent?
It
Like that 38.
represents
What?
it
Like I'm
represents the
still.
same number as the vertices plus the faces.
Okay, I don't think you're quite understanding what I'm trying to
Oh,
do
we have
here.
a whole hour to discuss it further. Please don't think it's just you. I guarantee there are many people that just don't want to speak up. So we will pause the video, but continue this discussion because it's very important.
Okay,
Okay.
so right here, so I'm looking